Assalamu alaikum and good afternoon to all. Today we are going to present a project about rewinding of a 4-pole 3-phase induction motor. Through this project, we have been grasped better understanding of the inner structure of induction motor, phase connection and phase sequence, and also the practical knowledge of rewinding a motor.
Before starting the project, we should know what a three-phase induction motor is. A three-phase induction motor is basically an AC motor which works by the principle of electromagnetic induction. An induction motor basically has two parts. Number one, the stator, and number two, the rotor. The stator is a static part which generates the magnetic field. The rotor is the moving part of the motor. Now, the question arises how the rotor rotates. At first, a three-phase AC input is supplied to the stator, which creates a rotating magnetic field in the stator. As a result, a torque is induced in the rotor. And as a result of the induced torque, the rotor starts to change the RMF, or the rotating magnetic field of the stator, and thus the rotor continues to rotate.
The steps we followed in our project are removal of the wirings, cleaning and insulating the slots of stator, then inserting stator coils in the slots, and connection of wire to get our desirable output. Finally, testing our motor to compare it with its initial ratings.
From the nameplate rating, we can see that our motor is a 380 volt, 50 Hz, 4-pole Y-connected induction motor rated at 0.5 horsepower. Also, the rated speed is 1450 revolution per minute. After disassembling the motor, we can see that it consists of three major parts: the stator shell, the rotor, and the wiring.
Here we can see the wire data used in connection and fiber data that is used for insulation in post connection. Here, before the rewinding process, the weight of the coils was 700 gram, and after it is 800 gram. And SWZ, or standard wire gauge, was 27, and after it is 28. Cross-sectional area of the coil was 0.132 millimeter square, and after it is 0.159 millimeter square. Before, the turns of the coil was 162, and after it is 170. Fiber data we used, that was before 2 ounce and after it is 1 ounce. Insulating tube used in the rewinding process is 1 millimeter, that is 5 pieces, and 2 millimeter, 3 pieces, 3 millimeter, 1 piece.
From this slide onwards, we will show our rewiring process and the theory behind it. A very short video of our rewiring in the stator slot is now shown. Here, the stator shell has 24 slots for wire placement. As the motor is a 4-pole machine, we shall have 4 magnetic poles in north-south order. The coils will be connected such that a magnetic south will be connected to its preceding north, and so on, to ensure that there will be no same polarity connection, otherwise the motor will not operate. In total, we have 12 coil windings for 3 phases, each phase consisting of 4 coil windings. If we cut the stator shell and lay it on its circumference, we shall get a slot positioning similar to shown diagram. We have arbitrarily selected any one of the slots to be labeled as 1, and the consecutive slots were labeled with succeeding numerical values. For phase A, we insert a coil winding such that it covers slot 1 and 6. The next slot covers 7 and 12, and the consecutive coil windings cover slot 13 and 18, 19 and 24 respectively. With assumption that the clockwise winding is north and counterclockwise winding is south, we can say that if clockwise winding covering 1 and 6 is north and counterclockwise winding covering 12 and 7 is south, we connect the coil winding coming out of slot 6 to the end of coil winding of slot 12. Following the same principle, we connect the coil winding from slot 7 to slot 13, slot 18 to slot 24. In the same way, we put our coil windings in the slot for phase B and phase C. For phase B, the winding covers slot 5 and 10, 11 and 16, 17 and 22, 23 and 4. For phase C, the winding covers slots 9 and 14, 5 and 20, 15 and 20, 21 and 2, 3 and 8. The three-phase power is supplied to the ends of each phase. For phase A, power is supplied to the coil winding ends coming out of slot 1 and 90. For phase B, it is supplied to the coil windings ends coming out of slot 5 and 23. And for phase C, to the coil windings end coming out of slots 9 and 3. The following slides show us connecting the wires according to the explained process.
We placed coils in insulator slots. The preformed coils made by hand are placed inward in slots and inserted in metal rod after inserting insulating paper to get a grip in the slots as the rotor will be rotating. We see the phase connection present in the next slides, and also we find the phase connections of AVC in insulating paper that will be helpful in conducting no load test, DC test, and locked rotor test in that is described in the later slide. So here the trimming is really helpful us to understand which phase we are currently doing operation with. In our final assembly of wires, we find a better understanding and clear view of motor and the insulation present there. The insulating paper and also the phase present here, like we see in the three-phase connection, the phase A, phase B, phase C, and A prime, B prime, C prime, gives a clear description of all the windings present here. In the final assembly, we see the pins present here. The pins are really vital for connecting the motor in either delta or Y configuration. As we see in the third picture, that there is a connecting rod present there that makes the connection Y, and the individual connection makes the connection to be delta. So we see in the second one here, we have in our advanced machine laboratory of BUET, we conducted experiments using voltmeter, ammeter, wattmeter, and we find the result from by conducting these experiments. The AC ammeter, the AC voltmeter, the DC voltmeter are used in this experiment. We have also used the a multimeter to calculate the value of resistance here, and also a wattmeter to calculate power. All the connections were properly placed, and also we have conducted every single test successfully. The motor ran very well, and in the next slide we will be comparing our motor, our test experiment result with the rated value that we have seen previously in the nameplates. In the experiment, we have rigorously done same experiment over and over again to get an average value more closer to the nameplate reading value. Here in the experiment, we have done no load test, block rotor test, DC test. In no load test, we find the voltage to be 400 volt. That is approximately equal to the nameplate rating of the motor that we have previously bought. And in the lock rotor test, we see the current to be 1.5. That is perfectly in alignment of the current, that the rated current that we have seen in our nameplate reading. And also from the DC rotor test, DC test, we found the coil resistance to be approximately 30 to 31 ohm. That is also aligned. That also aligns with the rated value that is present there. So I would like to bring an end by introducing every single member of our group. So Aye Thein, please introduce yourself.
My name is Aye Thein Mong, ID 1806195.
My name is Saheeb. My ID is 1806170.
My name is Swmic Mojumdar. My ID is 1806175.
This is Rudmila Rahman. My ID is 1806190.
This is Adib Md Tawsif. My ID is 1806185.
This is Mohammad Rokon, ID 1806180.
I'm Maliha Firdaus, ID 1806165.
Thank you so much for listening to our project video. Thank you.